Hello. So in this lecture, we will discuss about preliminary of HPC clusters, primary hardware aspect. Okay. So what is HPC cluster? So we are aware of laptops, desktops, no, but what is this HPC or what is this supercomputer? So they are different. They are more powerful, and they do more complex tasks. So uh, large computer systems are required for complex computing tasks. For example, uh, weather prediction. So the Earth is huge, and we need, in fact, data from all over the world for predicting weather in Kanpur. It's not local is not enough because the air is flowing from all sides, and Earth is getting heated from all sides. Anyway, so it's a very complex task, weather prediction. Banking, you need to serve millions of customers. Cloud storage, like you can imagine Google, how many billions of requests is handling per second. Social network, search engines. So both science as well as uh, social, uh, economic fronts and defense funds, we have complex tasks, and that requires faster and computers with can handle big data. So these machines are much more powerful than desktops and servers. And supercomputer or HP system can be thought of as a fast computer, specially designed or so it can be special designed, special hardware, or it could be many computers strung together. So you can have not quite laptops connected together, but faster CPUs than laptops, but you can have millions of them connected together, or many GPUs connected together. Okay. Anyway, so that's so there. I'm going to come to this difference in the next slide. So, past designs till 1990s were well. I mean, these are the days when the CPUs were not that powerful, and we had some 4 CPUs working together and things like that. Okay, so this person called Seymour Cray, okay, he is considered to be a key figure or father of supercomputers. So he had very clever ideas how to speed things up. So he says anybody can build fast CPU, but his trick is to build a fast system. So we discussed, no, I mean CPU speed is not the only thing. So RAM speed, connecting together, and uh, I mean the bus connections, all that are critical. And if you have many CPUs, how should they work together? Okay. Now he has another important quote. If you're plowing a field, like agriculture field, I'm not sure you've seen them, but it used to be done by animals in the past. Now tractors do it, but anyway, in the olden times, animals used to be used for plowing a field. So a strong oxen, the bulls, or so do you want 2 strong oxen or 1,000 chickens? So means of course you may think that you need strong oxen. So that was his design principle or the drive. So Cray came up with super machines, super CPUs, so which were 10 times faster or 100 times faster than what was available at that time. So there are a lot of innovations in CPU by him. So we'll just look at some of the innovations. Okay, so Cray was in favor of this, but it turned out special hardware will require special manufacturing, and that makes it expensive. So televisions are cheap. Why? Because they're selling in millions. But if you have special uh, a display unit, if you want to order one for yourself, it will cost you 100 times more or even more longer, because they had to design a new fabrication unit only for you. So the basic idea right now is to use off-the-shelf CPUs and put them together, so it's cheaper anyway. So the present design is chickens, okay. That's where it's gotten, but I would say things have changed a bit more. So this is Cray auction, then this is HPC Systems, many other stuff there, but now GPU has come, which is like auction, strong auction, okay. So maybe Cray's philosophy is back with GPUs, or quantum computers are like strong auction. They're very different design and they're special, okay. So anyway, so these are two principles. Do you need a special hardware, or do you want to work with standard hardware which can put many of them at work? So you don't need a genius to solve banking problem. You just need ordinary people, but many of them who can do it. So that's the present idea. But Cray was saying that you need a genius. Anyway, so that's the Cray. Now this is a very nice video about Cray. So I think I would want you to go to YouTube and watch this video. I will just stick to the.
Seymour Cray was an electronics engineer and one of the founding fathers of the supercomputer.
To watch this video, I will not do it here because of maybe copyright issues. So, but it's a very inspiring video. So you should see what innovations he brought in 90s, 80s and 90s. So Cray vector machine. So let's look at what is a Cray vector machine. So early days and servers, the CPUs were slow, and of course RAM was also slow. So he was coming with clever ideas to make the faster by simple trick. The trick was do many operations in a single cycle, which has become a norm now, but that was innovation. So instead of adding two numbers in a single clock cycle, you can add 8 pairs. So instead of A plus B C, so say AI plus BI CI, and I can go from 0 to 7 or 0 to 16. So these are called vector processing. So instead of scalars A and B added together and give C, I say AI plus BI is CI, and AI is a vector. So it's called vector operations, and we do it all the time now in modern ROM processor, as we discussed. It can do 16 vector operations per second, per clock cycle, not second, per clock cycle. So there is idea by Cray, which has become a norm in present CPUs, but it was done first time by him. Pipelining. I'm going to explain what is a pipeline in the next slide. So this is basically for vector operations. So AI, A0, B0, A1, B1, A2, B2, and they give the result. So this is the vector operation. In fact, when I was a student in 90s, there used to be a CPU, standard keyboard, they're called accelerators. Okay, so they were math accelerators. So that could do sine functions, some of these operations in a faster way. So these were special hardware. Anyway, now many of these have been imported to modern CPUs, and they become standard. Now let's look at pipelining. So it in fact is borrowed from industry. So Ford, Jerry Ford, I think Jerry Ford, the first Ford who was making cars. Ford made he in America, he was a guy who made car available for everybody. So to make it cheap, what he did was he created an assembly line. Okay, an assembly line where one guy will do only one task. So imagine that car's body is going from left to right, and one person will put one wheel, second person from the other side will put the second wheel. So the 4 people will put the wheels. Then it'll move to the next person who will put the steering. The next person will put the brake. So they'll just go in assembly line. But when it moves when the car moves from wheel to the steering guy, another car has come. for the person to put the wheels. So it just moves in assembly line, and so one person is expert in putting the wheel fast, and so it moves quickly, and you can generate more cars. In cloth industry, so they don't have tailors who does everything together, whereas one person is not done in cloth industry. One person cuts one part of the cloth, so he'll cut the left part, right part. One guy will do the stitching, and the third guy will put the buttons. So it's done in streamline. It moves quickly, and some of it is automated too, done by robot. Anyway, so let's see how it is done for number crunching. So here is the table. So clock cycle 1. So we need to do AI plus BI equal to CI, okay? But not vector, but in pipelining. So whether this can also be done vector, but it's doing vector plus pipelining. You should see that how it is done. So in first clock cycle, A1 and B1, these two numbers will come. So this segment 1, this is like place 1 for industry, this is like, so it's flowing into register R1 and R2, A1 and B1. Now in the clock cycle 2, R3 and R4 registers will multiply, R3 will multiply A1 and, so A1 and B1 will multiply it and stored in R3. R3 has A1, B1 product, and R4 will contain C1. Okay. Now in this time, R1 and R2 have become free. Okay, because the data has I need the product. In fact, I need AI plus BI, AI star BI plus CI. Okay, so A1 and B1 are not required anymore. So R1 and R2 are free. So A2 and B2 can flow in or from cache. Okay, so A2, B2 has flown in, and in this same cycle, R3 is filled up by A1, B1, and R4 is filled up by C1. Okay. Now what happens in cycle 3? Now you should see. So my R3 has this, R4 has C1. So now add them together, and so add this product with C1. So this is my result: A1, B1 plus C1. Now in this cycle, A2, B2 is multiplied and put in R3, because R3 has become free, because A1, B1 and C1 they have been added, and R4 also has become free. So R4 has C2. Okay, so we are ready with A2, B2 and C2. Now R1, R2 has also become free. So A3, B3 is flowing in from cache. Okay, so this goes on. So you are doing 3 operations in one clock cycle in a clever way. So the process will be 3 times faster. Had you been doing A1, B1, then get C1, then multiply, it is not the great idea. So anyway, this is how industry works, modern industry, and I exported in computer industry. So this is the cleverness. You port the idea from one field to another field. Of course, in physics too, we do it. The statistical physics ideas go into high energy and vice versa. Anyway, so this is the pipeline. Okay, so the basic thing is that very clever ways are adopted for making computation fast, and so that's why these hardwares are quite complex, quite intricate, but they give pretty fast results. And this is hard work over centuries. Well, so not say 1 century. I think 1940s to present. Okay? So innovations at every level, every time, collected over time. Okay, thank you, and we stop here.